Hi everyone, this is Yang from Virginia Tech. I present our paper, Session Key Distribution Made Practical for CAN and CAN-FD Message Authentication. This work addresses the security issues of automotive communication networks, especially CAN and CAN-FD bus. Automotive communication networks are ubiquitous in modern vehicles for enabling vehicle communication between electronic control units or ECUs. In most vehicles nowadays, there are a whole bunch of different automotive communication networks, each responsible for different subsystem control. The most well-known of them, perhaps you have heard of before, is the Controller Area Network, or the CAN bus. The CAN bus has been the de facto standard for the control of powertrain units or other safety-critical subsystems. CAN-FD is a 2012 extension of CAN bus. It can accommodate faster data transmission. In this work, we focus on CAN and CAN-FD bus. The CAN and CAN-FD bus adopts a broadcast and a subscribe messaging paradigm. Each CAN or CAN-FD message only indicates the message ID, which has no information about the sender or the receiver ECU. When multiple message transmissions collide with each other, a mechanism called arbitration is used to resolve the conflict. Message with lower ID value gets higher priority. And in the physical layer, there lies a major difference between CAN and CAN-FD. The entire CAN message frame is transmitted in constant bit rate, while the payload portion of the CAN-FD frame can be transmitted in flexible and most likely higher bit rate. Automotive communication networks are predominantly designed for optimized communication speed, including the CAN and CAN-FD bus, but they are heavily criticized for their lack of security. Recently, there has been a series of high-profile attacks on vehicle internal systems. The attacker gets access to the internal control of a vehicle through either the OBD2 port or exposed wired or wireless bus interfaces. The attacker can eavesdrop, spoof messages with arbitrary content to critical ECUs, or simply knock off the ECUs. The root cause for this security debacle is there's no effective security mechanism at all in these protocols. In response to the security deficiency in autos, the AUTOSAR Association, which is a global development partnership of automotive interested parties, has provided software architecture for future automotive communication networks with built-in security measures. They include entity authentication, which means validating of the sender of the ensuing communication. And the second, message authentication, which guarantees the message integrity and authenticity and the resistance of replay attack. It also provides guidelines on crypto strength, such as the length of authentication keys and MAC. Notably missing from the specification is the establishment of session keys for the purpose of message authentication. Session key establishment is critical to the real-world deployment of any security systems and is also the focus of our work here. Actually, prior to AUTOSAR, there have been many proposals on CAN message authentication, and some of them have addressed key establishment. The three schemes in green, called ValiCAN, LEA, and ValCAN, are proposed after the AUTOSAR and thus compliant with this specification. When it comes to key usage in automotive bus, there have been three paradigms of key management systems from the prior work. First is one key for all. The second is one key for each message ID. And the third one is ECU pairwise keys. And only the second one key for each message ID, is AUTOSAR compliant because each message subscribed by a group of ECUs, they are shared the same key for the session for communication. AUTOSAR adopts this paradigm because it achieves message-specific keys and also saves from the extreme overhead which would happen from the ECU pairwise key establishment. And as for the techniques for key establishment, there are normally three different genres: key agreement, key derivation, and key distribution. As we will show later, our proposed key establishment protocol is a key distribution protocol because of the efficiency in communication and computation. So in this work, we propose a key management architecture first. The system model consists of N ECUs and M message IDs. Each ECUI has a subscription list of message IDs. So the goal here is for all ECUs that subscribe to message J will get a shared session key skj. The threat model contains the fact that the adversary can do message eavesdropping, tampering with the current messages, spoofing, and replaying in the bus. And to facilitate the real-world deployment in the cars, here we raise 4 practical requirements for the key establishment. First, it has to be lightweight in computation and storage. Second, it has to be efficient in communication. Third, it has to be AUTHOSAR compliant in terms of security requirements, and it must accommodate for the on-demand ECUs, which are those ECUs who will switch on during driving, not from the start. We propose a new entity called key server in our system. Key server is kind of like a central entity in the system that shares a long-term key with every ECU. And at first, it generates a bunch of session keys from 1 to m, and it maintains a 6-bit system epoch. So in the example on the right, ECU 1, 2, 3 subscribe to message 1, and ECU 1, 2 subscribe to message 2. So through session key distribution and epoch synchronization and ECU entity authentication, these are all the functionalities. In the end, each ECU will get the session keys for the message it subscribes. To achieve these goals, we design key distribution protocols. First of all, we identify 2 primitives. The first one is KDC, which stands for Key Distribution Center. The second one is SKT, which stands for Secret Sharing-Based Key Transfer. And we adapt them for session key distribution in CAN and CANFD bus. The first one, SKTC, is a baseline protocol, and the second one, SSKT, is our novel scheme, which achieves better communication efficiency. First, the baseline SKTC protocol. In a nutshell, the key server, or KS, use the long-term key for each ECU as key encryption key to encrypt each session key and send it to each ECU. And the epoch is used for freshness as required by the AUTHOSAR specification, and the MAC for verification of key deliveries. It works like this. In phase 1, key server generates the session keys. And in phase 2, KS delivers the session keys to the ECUs one by one for each session key. And in phase 3 confirmation, each ECU will send back a confirmation message to show that it has received the session keys it subscribed. And from these confirmation messages, KS can confirm their receipt of the session keys and then move on to turn on the vehicle. And for an on-demand ECU, when it switches on during driving, it will send the request message or RE message during the driving and a request for the session keys. So the baseline is pretty easy to understand. Here comes our second primitive called Secret Sharing-Based Key Transfer, or SKT. It was proposed in 2010, and the scheme itself is based on Shamir secret sharing. It assumes that each member I keeps a secret pair with the key server. So in the first place, each ECU sends a random challenge to the key server, and the key server will construct a polynomial based on the inputs. And then KS broadcasts T public auxiliary points on the polynomial, which will be used by every ECU to recover the polynomial, and as well as the secret key, which is the points with x coordinate 0. To give you a rough example of how the math works, first of all, each ECU keeps its secret, and the challenges will be added to the y coordinates, secret y, as an offset. The session key and the secret points, the red ones, will be used to generate a polynomial by the KS. KS randomly choose another T auxiliary points on the polynomial. At the ECU end, the polynomial can be recovered from the only secret the ECU has, along with the T public auxiliary points. So in this way, one can recover the session key. The computation can be done by Lagrange interpolation on these t+1 points, which is shown here. And the product term here is known as a Lagrange coefficient. If the ECUs wants to establish another session key, it will just use another batch of random challenges and form another polynomial. When it comes to using SKT in practical scenario, SKT has a clear advantage in communication efficiency because of its broadcast nature, but it also has a disadvantage. It's all about the finite field arithmetic. The polynomial operation has to be done in a finite field. In the original SKT primitive, the finite field used has to be very large. It needs to be a product of two very large primes. It is used for resisting the insider spoofing attack, and the security relies on the intractability of large number of factorization like in public crypto. So W should be very large, likely thousands of bits long, to achieve the same level of security like public crypto, and is clearly impractical for resource-constrained ECUs. So in this work, we adapt the SKT primitive into our scheme SSKT for practical session key distribution in CAN and CANFD bus. First of all, for every 128-bit long secret key, it is dissected into 16 bytes, and every byte will be treated with its own polynomial. So in this way, the polynomial operation for each byte can be done within the Galois field 256, and we can achieve reduced computation complexity, but we need to assume that the size of each message group has to be fewer than 128 to use byte-wise operation in GF256. And secondly, to address the insider spoofing attack from the previous slide, instead of letting the ECUs to send random challenge to the key server, we let the key server to generate random challenges and send it back to the ECU. And these challenges, which are known publicly, will be used to derive secrets at the ECU end for polynomial recovery. SSKT works like this. The long-term key, which is kept by the key server and each ECU, is now a key pair denoted by X and Y. The ECU recovers session key segments by Lagrange polynomial interpolation in this finite field. In phase 1 key generation, key server generates the two session keys. In phase 2 preparation, key server will randomize 3 challenges and send it to each ECU separately. The random challenge will be used by each ECU to derive its own random secret for polynomial recovery for each message ID it subscribes. And in phase 3 key delivery, first key server generates the polynomials accordingly, and then it broadcasts a KD message like this. Each ECU can recover the session key from the key materials received from the KD message and its own secrets, like this. So for every byte from 1 to 16, it interpolates the corresponding byte of the session key from the TJ auxiliary points, which is shown in the KD message, and its local secret, which is the long-term key pair, except for the Y coordinates has been offset with the random secret. Then the session key for message J can be simply concatenated from those bytes, and this key can be verified with the MAC. And in phase 4 confirmation, it is the same as in SKDC that each ECU sends back a confirm message to KS, and the key server verifies the confirmation messages and turns on the vehicle. So similar to SKDC, product message has to be sent in separate frames if the payload size is too large, and the on-demand ECUs can send the request message during driving and can be accommodated for with a KD message. Both SKDC and SSKT achieves session key correctness, session key confidentiality, and ECU integrity and liveness. You can refer to the paper for more detailed discussion on the security. And especially, the third one also indicates ECU entity authentication, which is suggested by the ACSAC specification because of the confirmation phase we use. We implemented the 2 protocols for CAN bus deployment. We acknowledge that because the KNFD hardware is currently not available commercially. So this implementation is only for CAN bus. So for each protocol, we provide a key server program and node program. The node is just a normal ECU. The programs are written in Arduino IDE in C++, and two third-party libraries are used, including the Arduino cryptography library and the Seed Studio CAN bus shield library. Our code is available in GitHub. We made further optimization for SSKT for efficiency purposes. First, we use lookup tables to implement the GF256 arithmetic, a table for inverse, a table for exponentiation, and a table for logarithm. The last two are used for realizing multiplication. Second, we let each ECU to pre-compute the Lagrange coefficients. So in this way, we effectively trade memory for speed. We built a test platform with CAN bus. In this platform, there are n ECUs. Each of them subscribes to all the m message IDs. We configure that n takes value from 1 to 6, and m takes value from 1 and 6. We use Arduino Uno to simulate an ECU node, and we use Arduino Duo, which has a more powerful processor, to simulate a key server. And every board is attached to a CAN shield as a CAN protocol stack. We connected all the boards to a laptop to collect the information and the statistics. So here is the result. First of all, there is a little trick in the implementation. We minimized the inter-KD message delay at the key server while ensuring ECUs receive every message in full. So as a result, the message pipeline is tightly skewed to achieve maximum efficiency in time. And when m equals to 6, we have found the optimal KD delay for the two schemes while ensuring the stability of our test platform. In the result below, we can see that when m equals to 1, SKTC has a performance advantage, but when m equals to 6 and n is larger than 4, SSKT begins to show an advantage. And SSKT's advantage will continue scaling up for larger m and n. This is contributed by its better communication efficiency in the key delivery phase. But here, the maximum n we can try stops at 5 because of a memory limitation of Arduino Uno. To circumvent the hardware limitation of our platform, we perform extrapolation analysis on computation workload and communication overhead. On computation workload, first we benchmark the runtime of crypto operations on the normal ECU. Here we assume both Uno and Duo can be used as ECU. And the result below shows the extrapolated result of ECU computation workload in one protocol session. When Arduino Uno is used as ECU, SSKT begins to show advantage when m surpasses 12. And when Arduino Duo is used as ECU, SSKT shows advantage for all m values. Here we need to point out that this advantage of SSKT in computation is achieved at extra memory cost. Then we analyzed another metric, communication overhead. We first count the size of each protocol message in terms of CAN bits and their occurrence in one protocol session. The result is shown in the left table. And then we move to extrapolate the overall communication overhead for one protocol session. The result on the right shows SSKT has a clear advantage over SKTC in communication efficiency, especially for large M and a KNFD bus is used. This verifies our intuition in the first place that SSKT would achieve communication advantage. Here we argue that communication overhead is of more concern than computation workload, which is shown in the last slide, because the communication overhead is largely capped by the bus infrastructure, so there is little room for improvement. So therefore, we consider SSKT's advantage in communication a highlight for its potential deployment. To conclude, we first proposed a key management framework for ECU message authentication. And then we proposed two session key distribution protocols, the baseline SKTC and a secret sharing based SSKT, which has better communication efficiency. we implemented the two protocols and evaluated their performance with hardware test platform and also extrapolation analysis. In future work, we will continue work on the following issues of ACSAC-KT. First, how to achieve better memory efficiency, potentially with more efficient cryptography. Second, how to accommodate for larger group size in ACSAC-KT because currently the group size limit is 128. So we're going to do this potentially with larger finite fields as well as more efficient polynomial operations. Thank you.